talking about forces. A force can be defined as a push or pull on an object that causes the object to accelerate. The first force we are going to be talking about is gravity. Gravity is a field force. This means that gravity does not need to be directly touching an object in order to cause the object to accelerate. Gravitational potential energy is created by the elevated counterweight in our trebuchet. Gravitational potential energy is calculated by multiplying the mass, the acceleration due to gravity, which is 9.81 meters per second squared, and height. Energy transfer occurs when gravity causes the counterweight to fall once the trigger mechanism is activated. In this process, potential energy is created into kinetic energy. The gravitational force the counterweight experiences causes the smaller end of the arm to rise and the egg to launch. The falling counterweight transfers energy through the lever and sling.
Centripetal force. Centripetal force is inward acting force that keeps the projectile and sling moving in a circular path. This force is created by the tension acting on the sling. Centripetal force keeps the egg inside the sling. Newton's first law would predict the egg would fly out in a straight line, but the inward force exerted by the string keeps the egg going in a circular path. Tension from the sling provides centripetal force that keeps the egg moving in a circle. The double pendulum system is the sling that's connected to the longer arm. It increases velocity because the sling has its own rotational motion relative to the end of the arm. The centripetal force pulls the sling and projectile inwards towards their respective pivot points. Tension in the sling creates a force that acts on the egg, causing it to be pulled towards the end of the throwing arm. The tension provides the centripetal force. The total acceleration is the combination of centripetal acceleration and tangential acceleration caused by falling counterweight.
The next force is torque. Torque causes angular acceleration. Angular acceleration is the rate at which an object speeds up in its rotational path, slows down in its rotational path, or changes the direction of its rotation. This is caused by torque, which is a rotational force. The counterweight falling causes the trebuchet arm to rotate, creating torque. The magnitude of the torque is dependent on the force of the counterweight, the length of the arm, and the angle of the arm before the weight is dropped. The counterweight provides torque that rotates the arm of the trebuchet. When the torque the counterweight exerts is greater than the opposing torques, the arm rotates. Rotational inertia resists acceleration that torque causes. A larger counterweight and longer arm create more torque. When there is a net torque that is not equal to zero, angular acceleration occurs. The magnitude is proportional to the net torque.
Friction is a non-conservative force that reduces the efficiency of the trebuchet. It converts mechanical energy into heat. The first point where friction occurs is fulcrum, is when the counterweight falls, torque is exerted on the throwing arm and the axle. Friction resists the rotation. The second point where friction occurs is track. It is fraction between the projectile and the path it takes, v equals before it leaves the ground. The third where friction takes place is the sling release. The sling that holds the projectile exiting the hook involves friction. Energy is lost in this release.
The next force is the force of tension. Tension is a contact force, meaning that tension has to be touching an object in order to cause it to accelerate. The tension provides centripetal force, which is inward force. The egg's inertia causes it to resist the change in motion. The centripetal force provided by tension pulls the egg inwards and keeps it going in a circular path. The double pendulum effect is formed by the sling and the throwing arm. After the counterweight drops, the tension in the sling is significantly higher than the projectile's weight. This causes the projectile to be accelerated due to the torque from the counterweight. If the tension was not greater than the projectile's weight, the projectile would drop out of the swing. At approximately 45 degrees from the horizontal, tension stops being present in the sling and it flies. Tension allows our trigger mechanism to work by holding down the throwing arm and preventing our projectile from launching until we want it to.
In these diagrams, you can see that when the launch angle is at 45 degrees, the horizontal component of velocity and the initial vertical component of velocity are equivalent. Then you can see how when there's a greater launch angle, the horizontal component is much lower and the vertical component of velocity is much higher. This is not optimal because the equation distance equals velocity in the x direction times time shows that if horizontal velocity is lower, the range will be lower. In this diagram, you can see that when the launch angle is smaller, the horizontal component of velocity is greater, but the initial vertical velocity is lower. This is a problem because the vertical velocity correlates to time. So if the initial vertical velocity is lower, time will be a smaller amount. So when you do the equation distance equals velocity in the x direction times time, distance in the x direction will be lower if time is a smaller number. This diagram shows that a 45-degree angle is the most optimal combination of horizontal velocity and vertical velocity. The equal horizontal and vertical components of the projectile allows the horizontal speed and time of the projectile in the air to be as great as possible.
The next physics principle that is present in our trebuchet is rotational dynamics. Studying rotational dynamics can be defined as analyzing the forces and torques that cause an object to rotate around an axis. Torque is produced by gravity acting on the counterweight, making the arm of the trebuchet rotate. Angular momentum is the product of the moment of inertia and the angular velocity. The moment of inertia is the measurement of an object's resistance to rotational acceleration. Potential energy is converted to angular velocity in the arm and sling as the counterweight drops. Due to the relatively small mass and large radius of rotation, the sling and projectile receive a large portion of kinetic energy. The kinetic energy causes the angular velocity of the arm to increase. Rotational inertia is the object's resistance to angular acceleration. The double pendulum effect transfers rotational energy to the projectile, giving it a higher velocity compared to the rest of the throwing arm.
Now I'm going to walk you through the physics equation that is shown in the image below. We are given a few pieces of information about an object's flight path. We know the horizontal distance, or dx, is 3.6 meters, and the time of the object is in the air, or t, is 0.29 seconds. We also know the angle of the launch, theta, is 63 degrees. Our goal is to find the initial velocity of the object, which is v. To do this, we need to find the horizontal and vertical components of the velocity. First, let's look at the horizontal component vx. Since we know the horizontal distance and the time, we can use the formula dx equals vx times t. We substitute our known values, 3.6 meters equals vx times 29 seconds. Solving for vx, we divide 3.6 by 0.29, which gives us the horizontal velocity of approximately 12.41 meters per second. Next, we can use the trigonometry to find the initial velocity v. We know that the horizontal component vx is equal to the initial velocity v multiplied by the cosine of the angle. So vx equals v times cosine vega. We can rearrange this to solve for v. V equals vx times cosine theta. Plugging in our numbers, v equals 12.41 meters per second cosine 63 degrees. This calculation gives us the initial velocity, v, of 27.34 meters per second. So the final answer is that the object was launched with an initial velocity of 27.34 meters per second at an angle of 63 degrees above the horizontal.